You know that moment when you're looking at a flight tracker map, maybe online, and you see the path and it's this huge, like, curve.
Hmm.
And you just think instinctively, wait, shouldn't that be a straight line? I mean, especially when we're so used to, local maps where straight is shortest. What's with that?
Yeah, it's a totally natural question to ask. Our everyday experience,
Mm-hmm.
getting around town or looking at a regional map, it conditions us.
Hmm.
We think flat, we think straight lines are the way to go.
Okay, well, prepare for maybe a bit of a perspective shift today, because in this deep dive, we're really going to get to the bottom of why those airplane routes often look, well, curved,
Yeah,
and why thinking about it on a globe actually makes way more sense for these long trips.
right.
Our mission really is to demystify these flight paths. We'll dig into the geometry, the actual shape of our planet, and crucially, how trying to flatten that shape onto a map inevitably messes things up, visually at least.
And we'll tackle some of the common misunderstandings that tend to pop up around this whole topic, stuff you might have seen floating around.
Sounds good.
Yeah.
So we'll start with this idea of great circles. You mentioned they're like the Earth's natural straight lines.
That's the core concept, yeah. Great circles will explain what they are and why they're absolutely vital for flying efficiently.
And then maps, how they confuse us.
Exactly. We'll look at how flat map projections, especially the really common one, Mercator, can seriously mislead our eyes.
Okay.
We'll also touch on some other maps, ones actually designed more for aviation, and then wrap up by looking at some specific flight path examples and claims people make.
Okay, great circles. Sounds fundamental. So break it down for us. What exactly is a great circle, and why is it the go-to for flying, say, LA to Tokyo?
Right. So imagine the absolute most direct way you can connect 2 points on the surface of a ball, like the Earth. That's basically a great circle path.
Okay.
Technically, it's any circle you draw on a sphere where the circle's center is the same as the sphere's center. Think about the equator. That's a perfect great circle.
Right.
And all lines of longitude, the meridians, they all run pole to pole, cutting through the Earth's center. So they're great circles, too. Sometimes you'll also hear the term geodesic used for the shortest paths on curved surfaces.
So it's not arbitrary then. When an airline charts that big arc across the Pacific, they're following this geometric principle.
Precisely. It's not just a random choice or some scenic route. On a flat surface, like a piece of paper, basic geometry tells us the straight line is shortest. But our planet isn't flat.
It's definitely not.
Right.
Yeah.
So on a curved surface like our Earth, the straightest and therefore shortest path follows the arc of one of these great circles. If you try to fly what looks straight on some flat maps, that's often a rum line.
Rum line.
Yeah, a line of constant compass bearing. Easy to follow maybe, but usually longer over big distances. Unless, by chance, it happens to be the equator or a meridian. Then it's both.
Okay, theoretically that clicks, but practically for the airline, for the plane, how much difference does it really make flying a great circle versus something else?
Oh, it's huge. Really substantial. Flying the shortest possible distance means, quite simply, using less fuel, and it means shorter flight times.
Which passengers definitely appreciate.
Absolutely. And for airlines, fuel is a massive cost. So efficiency is key for their bottom line in scheduling. Modern planes use GNSS global navigation satellite systems, like GPS, to constantly calculate and follow these great circle paths with incredible accuracy.
So it's good for the wallet, good for the schedule, and I guess good for the environment too. Less fuel burn.
Exactly. The economic benefits go hand in hand with environmental ones. Less fuel means fewer emissions. It's a win-win in that sense.
You mentioned a way to visualize this earlier, the string on a globe idea. Can you walk us through that?
Yeah, it's a great little mental model. Imagine you have an actual globe, a physical one, and a piece of string.
Okay.
If you pick any two cities, say London and New York, and stretch that string tightly between them, right across the surface of the globe, the path that string takes, that is the Great Circle route. It physically shows you the shortest distance because the string pulls taut along the most direct path on that curved surface. It really helps make it intuitive.
I like that. Okay, I'm getting the globe picture. But then, yeah, we look at a flat map, the kind we see everywhere, and those shorting paths look all bent and weird. What's the disconnect there?
Right, and that's the fundamental problem. Representing something spherical, three-dimensional, onto a flat, two-dimensional surface. It's mathematically impossible to do it perfectly without some kind of distortion.
Like trying to flatten an orange peel?
Exactly like that. You can't flatten the orange peel without tearing it or stretching it or wrinkling it up, right? The same thing happens when we make a flat map of the Earth. We have to distort the surface in some way.
So wait, all flat maps are wrong in some way.
In a sense, yes. Every single map projection, which is just the mathematical method used to translate points from the globe onto the flat map, will distort something. It might be the shape of countries, or their relative size, area, or the distances between places, or the directions. You can't preserve all four perfectly.
So cartographers have to choose what to mess up.
Pretty much. They pick a projection based on what the map is for. If you need accurate shapes for coastlines, you pick one projection. If you need accurate areas for comparing country sizes, you pick another. If you need it for navigation by compass bearing, well, that brings us to Mercator. But we, as map users, often don't think about these built-in trade-offs.
Okay, let's focus on that one then. The Mercator projection. It's everywhere, especially online, right? What's its deal? What does it do well? And where does it fall down?
Right, Mercator. Developed way back in the 16th century, primarily for ships. It's a cylindrical projection. Its big advantage and why sailors loved it is that it's conformal.
Conform.
Means it preserves local angles and shapes. So if you zoom right in, the shape of a bay or a small island looks correct. And crucially for navigation back then, lines of constant compass bearing those rum lines we mentioned appear as perfectly straight lines on a Mercator map.
Oh, okay. So a captain could just draw a straight line, keep the ship pointed at that compass bearing, and eventually get there.
Exactly.
Okay.
Super useful for navigating before sophisticated computers. That's why it became so dominant.
But there's a catch, right? You said all maps distort something. What does Mercator distort?
The big one is size and area.
Ah.
Especially you get further away from the equator towards the poles, the distortion becomes massive.
That Greenland versus Africa thing.
That's the classic example. On a Mercator map, Greenland looks gigantic, easily as big as Africa. But in reality, Africa is about 14 times bigger than Greenland.
Wow, 14 times.
Yeah. And Antarctica looks like this enormous continent stretching across the entire bottom of the map. Distances near the poles also get hugely exaggerated. It's kind of wild how this map, designed centuries ago for a specific purpose, still shapes how many of us intuitively picture the world.
Okay, so connect the dots for me. How does that distortion make the Great Circle flight paths look so curved on a Mercator map?
It's because of how Mercator achieves those straight rum lines. It has to stretch things out horizontally, east-west, more and more as you go towards the poles.
To keep the longitude lines parallel.
Exactly. On a globe, lines of longitude converge. They all meet at the poles. Mercator makes them parallel lines. To do that, it has to stretch the space between them further north or south you go.
Okay.
So a path that's the actual shortest distance on the globe, the Great Circle, which might cut across those lines of longitude at varying angles, has to be shown as a curve on the stretched out Mercator grid to connect the right start and end points relative to everything else.
So the visually straight line I might draw on my screen between two cities on Google Maps?
That's usually a rum line on the standard Mercator view. And over long distances, that rum line is almost always a longer journey than the Great Circle path, which looks curved on that same map.
It's like map is tricking our intuition. Because
Yeah.
it's so common, we've just sort of absorbed its weirdness without realizing it.
That's pretty much what people mean by the Mercator paradox. It was useful, historically, for navigation by bearing. And it's still used online a lot for technical reasons, ease of tiling map sections, things like that.
Right.
So yeah, we've all kind of internalized this distorted view. Then we see a real flight path, a great circle arching way up north, and it feels wrong. It clashes with that ingrained map sense.
Are there other maps then? Projections that pilots or airlines actually use more often?
Oh, absolutely. Aviation uses projections better suited for their needs. A really common one, especially for charts covering areas like the US or Europe, is the Lambert Conformal Conic, LCC.
Lambert Conformal Conic. Okay, what's good about that one?
Well, like Mercator, it's conformal, so it preserves those local angles and shapes well, which is important for navigation. But its big win for aviation is that over typical flight distances in the mid-latitudes, great circles appear almost as straight lines, much straighter than on a Mercator. This makes plotting and visualizing routes much easier for pilots.
How does it do that? Is it still a cylinder?
No, think of a cone instead. Imagine placing a cone over the globe, sort of like a hat. It touches the globe along one or two lines of latitude, the standard parallels.
Okay.
Distortion is minimized near those standard parallels. So for a region like North America, you can set the standard parallels strategically, and the map is very accurate for shape and distance across most of the continent. Great circles look pretty straight within that zone.
Interesting. Different shape, different trade-offs. What about those maps that look like a target? Everything's spreading out from the center.
That sounds like an azimuthal equidistant projection.
Azimuthal,
Yeah.
equidistant. Got it.
Yeah, its unique feature is that distances and directions from the center point of the map are true. So if you have one centered on, say, the North Pole,
Okay.
the distance and bearing from the North Pole to London or Tokyo or anywhere else will be shown correctly on that map.
That sounds useful, but what's the catch this time?
The catch is everywhere else gets distorted. Shapes, areas, and distances or directions between any 2 points that aren't the center get warped, often quite severely, the further you move away from that central point.
So good for seeing things relative to one spot, but bad for overall shapes.
Exactly. You sometimes see these used in, let's say, less mainstream discussions about the Earth's shape. They can be centered in a way that makes certain routes look like straight lines on that specific map. But it's misleading because the rest of the map is so heavily distorted. Think of it like stretching a rubber sheet just from the middle. The center stays okay, but the edges get really warped.
Right. It really drives home the point, doesn't it? That map choice is everything. They're tools, specialized tools, and you have to know what they're good at and what they're, well, distorting.
Precisely. No flat map is perfect. Understanding the projection is key to correctly interpreting what you're seeing, especially with something like flight paths.
Okay, let's pivot a bit and tackle some common questions and maybe some alternative explanations people offer. First one, and we sort of covered it, but let's hit it directly. Why do direct flights look so curved on flight trackers? Like really dramatically curved sometimes.
Yeah, and it comes back to what we just discussed. Most of those online trackers, the ones you pull up on your phone or computer, they overwhelmingly use map displays based on or very similar to the Mercator projection. It's just convenient for web display.
So it's the map, not the flight path.
It's the map representing the flight path. That path, say New York to London, is the shortest route on the spherical Earth, a great circle. But when you project that inherently curved path onto the flat, distorted grid of the Mercator, literally at those higher latitudes, it looks like a big northward arc. Same for, say, San Francisco to Paris. It curves up towards the Arctic on the map.
But it's actually the straightest way to go on the globe.
It's the straightest way on the globe. The curve is an artifact of the map projection.
Got it. Okay, here's another one I've definitely heard. Do pilots constantly have to dip the nose down to follow the Earth's curve? Like they're always falling off a flat plane?
Right. That one pops up a lot, often in flat Earth arguments.
Yeah.
But no, that's not how it works.
So what is level flight?
Level flight just means maintaining a constant altitude above sea level. Think about it. Gravity is always pulling the plane down towards the Earth's center, and the wings are generating lift to counteract gravity. The pilot, or more often the autopilot, is constantly making tiny adjustments to keep those forces balanced and stay at the chosen altitude.
Okay, so how does that follow the curve?
Because gravity pulls towards the center of the sphere, and the air mass itself, the atmosphere, curves with the Earth. So by simply maintaining that constant altitude relative to the ground or sea level below, the plane naturally follows the curvature of the Earth. There's no conscious or continuous dipping the nose required specifically for the curve. Aerodynamics works with a spherical Earth.
That makes way more sense. Okay, what about the tech, the navigation systems inside the plane? Gyroscopes, those fancy AHRS systems, how do they handle the curve? Do they need constant resets?
Good question. So older gyroscopic instruments, like the artificial horizon, they use the principle of gyroscopic inertia. A spinning wheel wants to stay in its orientation. But they also had clever self-erecting mechanisms.
Self-erecting.
Yeah, using small weights or air jets, they'd sense the direction of gravity, which is always down towards the Earth's center, and slowly align themselves to the local vertical. So they inherently reference the spherical shape.
And modern systems, AHRS.
Attitude and heading reference systems, they're much more advanced. They typically combine data from different sensors, gyroscopes, often laser ring gyros or tiny MEMS ones, accelerometers, which sense both movement and the constant pull of gravity, and magnetometers for magnetic heading. Sophisticated algorithms process all this data together.
To figure out the plane's orientation.
Exactly. To calculate the aircraft's precise attitude, its pitch, roll, and yaw relative to the Earth's surface. These systems are designed from the ground up, knowing the Earth is a sphere. They use gravity and even the Earth's rotation rate as fundamental inputs. The curvature is built into their physics and calculations. No manual curve adjustment needed.
Wow. Okay, the tech is designed for the sphere. Now let's talk specific routes people point to. We hear arguments about flights in the southern hemisphere, like, say, Auckland in New Zealand to Buenos Aires in Argentina.
Ah, yes, the long southern hemisphere routes.
Yeah.
The claim you often hear from flat Earth proponents is that direct flights like that either don't exist, or if they did on their flat map model, they'd have to take some ridiculously long path, maybe way up north.
They do exist, right?
Oh, absolutely.
Yeah.
Airlines like Qantas and LATAM have operated routes like Santiago to Sydney or Auckland to Santiago, Buenos Aires. These are efficient, great circle paths on a globe cutting across the vast southern Pacific.
Like tense on a globe.
Completely. And crucially, the actual flight times for these routes match the distances calculated on a spherical Earth, not the hugely inflated distances you'd get trying to plot them on most flat Earth maps. There was even a famous Qantas flight, QF-14, a repatriation flight during COVID, that flew Buenos Aires to Darwin, Australia.
Yeah.
And its flight path went directly over Antarctica.
Mm-hmm.
A very southerly route, totally logical on a globe, impossible on their usual map model.
Okay, that's pretty compelling. What about another one, that Taiwan to Los Angeles flight that diverted to Anchorage, Alaska? That gets brought up a lot.
Right. The argument usually goes, look at our flat map. Anchorage is practically on the straight line between Taiwan and LA. Proof. But look at a globe. Or even just a better map projection for that route, like a conic one. The actual Great Circle path from Taiwan to LA arcs significantly northward. It passes relatively close to Alaska.
So diverting to Anchorage was the logical nearby option.
Exactly. If you have a medical emergency mid-flight, you divert to the nearest suitable airport along your actual flight path. Anchorage was right there on the Great Circle route they were flying. The flat map argument completely ignores how Great Circles work and relies on a distorted map to create a false impression.
It seems such a pattern. Okay, what about the general claims like flights always avoid Antarctica or all southern hemisphere long hauls have to stop up north? Any truth there?
Well, Antarctica is challenging extreme weather, remoteness. So routine scheduled passenger flights over the deep interior are rare, though not non-existent for some specialized flights or specific routes like that QF-14, but avoiding it entirely.
No. And the idea that you have to fly north to get between, say, Australia and South Africa?
Simply false.
Yeah.
There are plenty of direct long-haul flights connecting Australia, Southern Africa, and South America that stay entirely within the Southern Hemisphere. Think Johannesburg to Perth or Sao Paulo to Johannesburg. They follow southern Great Circle routes. The idea that everything is forced north is just not backed up by actual flight schedules.
So it really boils down to people not being familiar with map projections and spherical geometry, and maybe taking one often misleading flat map as the absolute truth.
That's a huge part of it, yes. These arguments often rely on showing you a specific, often unsuitable map projection that seems to support their point, ignoring all the others. They leverage the unfamiliarity and maybe play on a sort of that looks weird, it can't be right feeling, appealing to intuition that's been shaped by, well, imperfect maps.
Okay, so we've established great circles are the shortest geometric path, but I suspect the actual flight path logged by a plane isn't always a mathematically perfect great circle arc.
You suspect correctly. Absolutely right. The Great Circle is the theoretical ideal for distance. But real-world flight planning is way more complex. It's an optimization game with lots of factors. The final route is rarely, if ever, a pure Great Circle.
So what are the big things that make airlines deviate from that perfect shortest distance?
Probably the single biggest factor day-to-day is the wind, specifically the jet streams.
Ah, those super strong high-altitude winds.
Exactly. They mostly blow west to east. Airlines will absolutely adjust their routes, sometimes quite significantly, to catch a strong tailwind. It can save a lot of time and, crucially, a lot of fuel.
Like getting a free speed boost.
Pretty much. And conversely, they'll try hard to avoid flying directly into a strong headwind, even if it means taking a slightly longer path in terms of ground miles. That's a major reason why flights from North America to Europe, going east, are often noticeably faster than flights coming back west. You're working with or against those jet streams.
Makes total sense. A real no-brainer to use the wind. What else comes into play?
Weather is a huge one, obviously.
Yep.
Thunderstorms, hurricanes, large areas of turbulence, even volcanic ash clouds. Planes will make detours, sometimes big ones, to avoid those for safety and passenger comfort.
Right. Can't just fly through a hurricane.
Definitely not advised. Then there's the whole system of air traffic control, ATC, and airways. Airspace isn't a free-for-all. It's highly managed.
Like highways in the sky.
Sort of, yeah.
Yeah.
ATC directs planes along specific routes, defined by waypoints to keep everyone safely separated and maintain an orderly flow. Think about the North Atlantic tracks, the NAT tracks.
I've heard of those.
They're a prime example. They are corridors across the Atlantic that change position daily based on the jet stream and weather forecasts. Planes follow these tracks, which are designed to approximate the best Great Circle routes for that day while keeping everyone organized.
So structure imposed on the ideal path.
Exactly. Plus, you have restricted airspace military zones, sensitive government areas, temporary flight restrictions that commercial flights have to steer clear of.
And I think you mentioned something called ETOPS before. How does that fit in?
Right, ETOPS, Extended Range Twin-Engine Operational Performance Standards. Basically, rules about how far a twin-engine plane can fly from the nearest airport it could safely divert to in an emergency, especially over oceans or remote areas like deserts or poles.
Ah, so that might force a slightly less direct route sometimes to stay closer to potential diversion airports.
It can, yes. The route might need to be adjusted slightly to ensure the plane is always within the required ETOPS diversion distance from a suitable airfield. It adds another layer of constraint.
Any other factors? Maybe money.
Sometimes, yeah. Overflight fees. Countries charge airlines for using their airspace. Usually, it's not a huge factor compared to fuel savings from a direct route, but if there are two route options that are very similar in time and fuel burn, an airline might choose the one that avoids or minimizes fees in expensive airspace.
Wow. So flight planning software must be juggling all of this constantly.
Yeah.
Geometry, wind, weather, ATC, rules, costs.
It's incredibly sophisticated stuff. It's a massive, multi-objective optimization problem. They feed in all that data, the basic Great Circle path, the detailed wind and weather forecasts, the current ATC routes and restrictions, ETOPS requirements, costs, and the software calculates the optimal route considering everything.
Optimal meaning the best balance, not just shortest distance.
Exactly. The shortest distance is just one input. The final flight plan is the best compromise to be safe, efficient, legal, and reasonably comfortable. So yeah, almost never a perfect mathematical Great Circle, but the smartest path considering the real world.
This has been genuinely fascinating. So let's just circle back. We started wondering about those weird curved lines on flight trackers. And now we know it's mostly about trying to show our round Earth on a flat screen, right? The shortest path on the globe, the Great Circle, looks curved on many common maps, especially that Mercator one.
That's the main takeaway, yeah. Earth is a sphere, great circles are the shortest flight paths in theory, saving time and fuel. But flat maps, particularly Mercator, distort these paths visually. Other map projections used in aviation, like the Lambert conformal conic, show them more accurately for planning.
And we also busted some myths pilots aren't constantly dipping the nose. And those arguments about specific flight paths often just misunderstand the maps and the globe.
Right. They often stem from unfamiliarity with projections and spherical geometry. And we layered on the real-world factors wind, weather, ATC, ETOPS. I mean, the actual flown route is an optimized path, not just a pure geometric arc.
So if someone listening wants to really truly get this, to visualize it better, what's your top tip?
Honestly, get a physical globe. Or use a 3D digital tool like Google Earth, but make sure it's in the globe view, not the flat map view.
And then trace the routes.
Yeah. Take that piece of string again, or just use your finger. Trace the path between, say, New York and Rome, or Sydney and Johannesburg, on the actual globe. You'll immediately see why it arcs north or south the way it does. It becomes instantly clear that the curved line on the flat map is actually the straightest, most direct path on the sphere. It really helps bridge that intuition gap created by flat maps.
That's a fantastic practical suggestion. It really underscores how much we rely on these flat pictures and how they subtly shape how we see the world, maybe even beyond just flight paths.
It does make you wonder, doesn't it? How often our understanding of global issues, distances, relationships might be subtly influenced by the inherent distortions in the maps we see every day.
Definitely something to think about. Well, this has been incredibly insightful. Thanks so much for clearing the air on all this.
My pleasure. Always fun to talk maps and globes.